Hi everyone, welcome back. So in this particular video, we're going to continue with our discussions on the synthesis of alcohols, especially focusing on carbonyl compounds. And in the previous video, we looked at two methods for doing this. One was the hydrogenation reaction, which used hydrogen gas along with a metal catalyst, very similar to the hydrogenation of alkenes or alkynes. And then the second one was a new reagent that we learned, sodium borohydride. In this particular video, we're going to learn about a third reagent which allows us to do the same thing, and it is very similar to the sodium borohydride. This reagent is called lithium aluminum hydride. Okay. It is abbreviated as LAH. This reagent is also a source of nucleophilic hydride H minus. So very similar to the sodium borohydride. And even the structure of this reagent is very similar to sodium borohydride, where we now have a lithium cation and we have aluminum with 4 hydrides connected to it. And the aluminum has a formal negative charge. So very similar to the sodium borohydride, the lithium aluminum hydride could also, in principle, serve as a source of 4 hydride ions, okay, or 4 hydride nucleophiles. A key difference as far as lithium aluminum hydride is concerned is that this is reactive, okay, or it is more reactive compared to the sodium borohydride, okay? And this is moisture sensitive. So when you're doing a reaction with lithium aluminum hydride, you have to keep moisture away. It has to be done using dry solvents. You cannot have protic solvents around, okay? Moisture sensitive, so you cannot use protic solvents. It is pyrophoric, so it would catch fire when you have moisture around if it gets wet. So the reaction itself is done in 2 steps. Okay, so very similar to the sodium borohydride example. If you have a carbonyl compound, let's say you have RC double bond O, R prime. For the lithium aluminum hydride reaction, this reaction is done in 2 steps. The first step is when you react the carbonyl compound with lithium aluminum hydride. Okay, let me make it better. Lithium aluminum hydride using a polar aprotic solvent. Okay, so a good example is THF, tetrahydrofuran. This is an ether, and you can get this solvent, you can buy it as a dry solvent, or you can dry the solvent using sodium. By drying, I mean you can remove the moisture in it. So you can get the solvent in an anhydrous form, okay, with THF. And then you finish this reaction off using a water workup or an acidic workup. The purpose being the same, that serves as a source of proton. Now compare this to the sodium borohydride reaction where we use sodium borohydride in a polar protic solvent, which was the source of protons. So in this particular reaction, the key difference is you cannot have a source of protons along with your lithium aluminum hydride. That has to come in as a second step. Now, what does all of this mean? So this means if I'm doing a reaction, or if I'm doing this reaction, how my experiment would be set up is I would have a round bottom flask with my ketone or the aldehyde and the polar aprotic solvent in that round bottom flask. And then I'm going to add lithium aluminum hydride to it. That is the first step. And I'm going to let it react. And once all this carbonyl compound has reacted with the lithium aluminum hydride, okay, once I've made sure that this is all consumed, then I'm going to add water or acid to do. I'm going to do a water workup with it. But I cannot have any of this moisture or proton source around when the first step is going on. So that's what we mean by these two steps. By the end of it, we still get, we will get the alcohol product. So the product isn't any different from what we get in the case of sodium borohydride. So we get an alcohol product. Okay, mechanistically, again, it's very similar. So in the first step, you have lithium aluminum hydride, and the reactive part is the aluminum hydride, which is the source of your nucleophilic hydride. So very similar to the sodium borohydride, I'm going to take this hydrogen along with that electron pair. So my electron push starts from that bond because the hydrogen is taking the electron pair with it, goes and attacks the carbonyl carbon. Okay, because this carbon is del positive. That's where the electrophilic site is. This hydride is H minus, and that's where the electrophilic site is. So this is del positive. Okay, goes and attacks that carbonyl carbon. The double bond opens up to maintain octet, and at the end of it, we will get the alkoxide. So the hydrogen has added here, and we have an alkoxide. And then, so this is our first step, which is done using THF, that is just a solvent, okay? And then in the second step is where we bring in our acid or water. I'm going to use a hydronium ion to use to show acid, okay? So that's the source of protons. So now this alkoxide gets protonated, picks up a proton from that acid and gives me the alcohol, or gives us the alcohol product. So that's the mechanism, very similar to the sodium borohydride case. Important thing again to remember is that this reaction is done over 2 steps. Unlike sodium borohydride, the proton source is not present in the first step. It's only in the second step. Okay, let's do it. Let's try another example here again to show what is possible or how could we use it. If we have an asymmetric alcohol, like we did earlier, so let's say we have an asymmetric carbonyl compound, asymmetric carbonyl compound, say let's say ketone, and if we do the lithium aluminum hydride reaction on it, so lithium aluminum hydride in presence of THF, follow this up with some acidic workup, we will get the alcohol product, but this alcohol product is going to be a racemic mixture, okay? We're going to get a racemic mixture here because this carbonyl carbon is planar, so the attack again can happen from both faces of that carbonyl compound, so we get a racemic mixture. So that would be the reaction here, okay? Now, let's just summarize all 3 of these reactions and what are similarities and what are differences between them, okay? How could we use them and what would be the sort of products? So let's choose a carbonyl compound, maybe this compound here. That's a ketone, but notice there's also a double bond, an alkene in it, okay? So if we have a ketone like this, and if we do a catalytic hydrogenation on it, which was the first method for reducing that ketone. So if we do hydrogen gas with platinum, okay, And this reaction is usually done at high temperatures and pressures. When you do this reaction, you're going to get the alcohol. Okay, but so the carbonyl group would be reduced to the alcohol, but the alkene is also going to be reduced under these conditions because these are the exact conditions that we use for converting an alkene into an alkane. So both of those reactions would occur simultaneously. You won't be able to prevent this alkene from reducing under these conditions. Okay, so your product is going to be the alcohol, but the alkene is also gone. Now, if we do sodium borohydride, we use sodium borohydride with a polar protic solvent like methanol and alcohol as a solvent, our product is going to be the alcohol, but the unsaturation or the double bond is going to stay. That will not be gone. That is still going to be there. And if we do a lithium aluminum hydride reaction, so let's say LAH with THF, follow it with some acid workup, our product is going to be the same. So you notice how the sodium borohydride reduction and the lithium aluminum hydride reduction, they give us the identical product here. Now, this is in a scenario where there are no other functional groups present in your molecule. As we will see later, lithium aluminum hydride, because it is a stronger reducing agent, it can reduce other functional groups like carboxylic acid derivatives. Whereas sodium borohydride, because it's a weaker reducing agent, it is unable to do it. So each reagent has its advantages and disadvantages depending on what is it that you're going to accomplish here. Okay, but that was a short summary of all the reagents that we've learned for alcohol, for reducing a carbonyl compound into an alcohol, to synthesize alcohols from carbonyl compounds.